All right, let's look at our lesson for today. We're going to cover 1.7 and 1.8. These are the final two sections in the chapter. Lesson 1.7's essential question is, how is deductive reasoning used to prove a theorem? And at the end of this lesson, you'll be able to use deductive reasoning to prove theorems. And 1.8 says, what can you conclude when valid reasoning leads to a contradiction? What that is asking you is, what does it mean to create a proof by contradiction? Proof by contradiction and proof by counterexample are the two main proof methods we're going to use in this course. And at the end, you can say that you are able to use indirect reasoning to write a proof. This is the beginning of our second quarter writing assignment. And your second quarter writing assignment heavily relies on proving lines parallel. And that's what we're going to learn in chapter 2. And I have that set up that way for a reason, because I want you to have all the content done, tested, and time to talk it over with me before you start your quarter 2 writing assignment. But to do that, I got to introduce some new symbols, and these are symbols that we're going to need for today's lesson and for tonight's homework. Your first new symbol is parallel. In the textbook, it'll look like that. When I write it handwritten, they're usually slanted lines, and symbolically they look like that on a line, but more likely they're going to look like this. They're just arrows at that point. So this means these are parallel. These are no longer parallel, just like the tick marks, the number matters, and now they're parallel again. So let me show you what that would look like. So let's define this as line 1. And this one is line 2. Because of these marks right here, and they're the same number, I can say line 1 is parallel to line 2. And parallel just means they will continue, since they're lines, we know they continue forever in both directions. But parallel means on a flat surface, they will never intersect. In quarter 3, if you're doing really well in the class and you want a harder challenge for your writing assignment, we will look at curved surfaces and why our definition of parallel doesn't actually fit all cases. That's a much more advanced topic. I have had a few students tackle it, and they've done fairly well. You get a lot more leeway in that writing assignment. That is purely an effort assignment. I'll get more into that as we get closer to the third quarter writing assignment, but if this has piqued your interest, keep this in the back of your mind and come talk to me about parallel lines on non-Euclidean surfaces. All right, let's talk about perpendicular lines. So perpendicular lines meet at 90 degrees. And there's some nice things about that, and that is we know that the measure of this line here is 180, so if this is 90, this is 90. We also know if we were to continue this, this would be 90 and 90. So this shows us if we go all the way around, we get 360 degrees. And if you didn't know already, a circle is 360 degrees. So there is a little bit of a visual proof of how this works on a coordinate plane and why a circle is 360 degrees. But most importantly is that you know this symbol right here. So now let's draw two more lines. Let's call this line 3 and line 4. What you'll see me write is line 3 is perpendicular to line 4. So there's our new symbols for today. Let's move on to the actual lesson. Next slide, we're going to look at a 2-column proof. You will do a minimum of 3 of these on your writing assignment next quarter. Let's look at our 2-column proof. This is the first style we'll learn in this course. It's called a 2-column proof because it is 2 columns. It's a hypothesis column on the left and a conclusion column on the right. It's Remember, P is always your hypothesis, and Q is always your conclusion. Now, let's just read it. And you'll see that what I meant by writing mathematically as being a big part of this course is kind of looking us right in the face here. What we have here is line 1 is parallel to line 2, and that's our given, right? That means it's from our hypothesis. Line 3 intersects line 1 and line 2. That's also given. So let me draw that and show you what that would kind of look like on a problem. We're going to reverse engineer this. So here's a line, and here's a line. So we'll call these line 1 and line 2, and we know they need to be parallel. So I'm going to go ahead and add a parallel marker to each one so that we can see that that's what's given. And if we were given this and we were to say put this information into a 2-column proof, once I've labeled the lines, we can go ahead and do that. So now we have line 1 labeled, we have line 2 labeled, and we have shown that they are parallel. So here is everything here. So what this would look like written in a conditional is if line 1 is parallel to line 2. Of course, we'll have that written out in full sentences, but for brevity, let's leave it like this. So because it's in our hypothesis, it goes after the if, but before the then. And then we have line 3 intersects line 1 and 2. Also given, so then we're going to say, and line 3 intersects line 1 and line 2. So we need a third line here. So I'm going to go ahead and draw that third line in, and that line intersects. Notice it doesn't tell you at which angle it intersects, so we don't have to worry about that, and we can't add that information yet, right, because it's not in the given. So I'm going to call this line 3. And so far, we've now reverse engineered our hypothesis. And then if we want to look at it again, if I had just started with this diagram, I would just say what was given in the diagram. Line 1 is parallel to line 2, and line 3 intersects it. Both lines, and it doesn't say anything about the angle, so I haven't added any additional assumptions here. I'm going to change the color of my ink so we can talk about what we want to do. What this one is going to do now is I want to look at my conclusion, and my conclusion is always my last one. Whenever I have my then part, that's what we're working towards. And if we can start with our hypothesis and use known theorems, sometimes postulates and conjectures, I wouldn't do that for anything too serious. But if you just want to try and get from point A to point B, then we have to go back and look at our postulates and conjectures and try and do a proof of them. So avoid them at all costs. Go with knowns in math classes, theorems that we cover in this class, because we know theorems are always true. But our conclusion is then angle 2 is congruent to angle 1. So now we need to label these. And the nice thing about this is what we're concluding, right? This is what we're saying. So on this diagram, I have a little bit of freedom here to label this however I want. However, if I mislabel it, then we're going to show that we have a contradiction or that it's not true. So we need to be careful in how we label it. What we want to show is that 1 is congruent to 2. So what I'm going to do now is take a minute and look at this and see if I can reconstruct this drawing to match this. This is not something you'll have to do. I will give you the positioning of the angles and just ask you to prove it during this chapter. In chapter 2, you're going to have to do a little bit more of the lifting, but I have some knowledge right now that you don't with this theorem here. We know this one, and you guys should know everything else from either Algebra 1 or in my class so far. So the same side interior angles theorem tells us that if we have two lines that are parallel, then we have two angles on the inside of those, or on the interior, who are on the same side of the transversal. Line 3 is called the transversal And all the transversal means is it passes through a line, 2 lines, 3 lines, a number of lines. It transverses them. So if I break this down one more time, same side of the transversal, and on the interior of the parallel. Oh, we have a symbol for that, so I'm not going to spell it out anymore. So same side of the transversal and on the interior. So here's my parallels, and I can either use this side or this side of the transversal. So again, I have a lot of freedom here, but I'm going to go ahead and pick this and this for 1 and 3. And then I'm going to look at this right here, and it tells me that angle 2 plus angle 3 by the linear pairs theorem. Well, then now there's only one place that can go. Well, actually, there's 2, right? It can go here, or it can go here, because it can be a linear pair this way, or it can be a linear pair this way. I am more inclined to naturally choose this position only because the line's horizontal, and it's easier for me to see it in that fashion. So now I'm going to look at my next step, and we're just trying to prove that angle 2 and angle 1 are congruent. And to do that, we need to see if all of these steps hold true. Well, another nice thing about the same side interior angles theorem is that the 2 angles equal 180, and we'll actually prove that in topic 2. But for now, I just want to show you how this proof works. So the measure of angle 1 plus the measure of angle 3 does equal 180 by the same side interior angles theorem. So when you're writing your proof, you can kind of see now that in algebra, and this is what I kind of told you was going to be so different about this class. In algebra, we're going to give you that angle 1 is maybe 120 degrees and angle 3 is 60. And we're going to say, can you solve it? Or we're going to say angle 1 is 120 and angle 1 plus angle 3 equals 180. Here, we're doing it for any number, and this is where we start talking about generalizing what we're doing. All of this is very generalized. We can plug in any number for angle 1 here and solve for angle 3, and it holds for any value of angle 1 or angle 3. This is why it's called a proof. It works for any value if we can follow these steps and show all of them to be true for this case. If we adjust the transversal's angle, then it will be true for all cases. So this one checks out by the same side interior angles theorem. Measure of angle 2 plus the measure of angle 3. This one you're ready to verify. We know about the linear pairs theorem, and we can see it right here, and we've already kind of drawn our protractor of 180 degrees. So we can say this one's true. Now this is a little bit of an interesting one. This is a substitution property, right? If 2 things have the same value, I can substitute them in for each other. Well, if the measure of angle 1 plus the measure of angle 3 is equal to 180, and the measure of angle 2 plus the measure of angle 3 is equal to 180. And remember, this works for any measure of these 2. They're locked together. As this line rotates, right? If it had come in at any other angle, by the linear pairs theorem, it doesn't matter what that angle is. They'll still be 180 degrees when you add them together. So one thing we can do here is if they're both equal to 180, we can remove that value because we have our variables here, and we end up with measure of angle 1 plus the angle 3 plus the measure of angle 2 plus the measure of angle 3 are equal. Well, we can then subtract angle 3 from both sides because they're the same value, so we can balance the equation through the substitution property. We can then subtract the measure of angle 3 from both sides, and since the measure of angle 3 will always be equal to itself, it leaves us with the measure of angle 2 is equal to the measure of angle 1, and that, to get to that step, we had to do the subtraction property of equality. And what we were shooting for here is that angle 2 is congruent to angle 1, and that is the definition of congruent angles. So I have a few more of these to show you as we get going, but the whole idea here is to get the spirit of the 2-column proof down. It is you always start with your hypothesis as you're given, and then you move into any steps necessary to get closer and closer to your conclusion until it is all said and done. So a recap. This was given by a diagram. This was given by a diagram. It could also be given by a sentence like I had above. And then all of these theorems were used to prove this step. Now, one thing that I do, and I'm not going to require you to do because not all proofs do this, and this was just something from the university that I came from, they would make me rewrite this. And then here, because I started with a given, I would write conclusion. Now, I asked one of my professors why, Dr. Garman, and he told me that way I know you thought you were done, or you're telling me you're done. So if you missed anything, or if there was another step, I could provide you more accurate feedback by saying, yeah, you're almost there, but you're not quite there. It's going to look great on your paper if you go ahead and do that for me. I know it's an extra step. I'm not going to hold it against you if you don't, but it does, to me, and in the very few books that I've seen it, offer a more elegant end to your proof, because you are saying we've accomplished what we set out to do and we've reached our conclusion, or whatever came after then. One other thing you can do, and it only makes it easier to reference, if you get any more complicated, you can call this hypothesis 1, 2, 3. And the reason we can start calling these hypotheses is because something like this is already well known in math, right? We all know the substitution property. So we can say here that we can make substitutions based on these both being equal to 180. So really, it's not really telling you you're doing it here. The nice thing about calling this hypothesis 1 and 2 is that you can actually call back to what you're doing there. You don't have to do that either, but it does make for a more convincing paper. And if you're doing a more complex proof, it's actually easier to just reference back to, P5 to show that we did substitution and that we're recalling that for another step. So the next style of proof that we'll briefly go over here is the written paragraph proof. And this is going to be necessary for your second writing assignment as well. And I will provide you a template to fill out. I will provide you a lesson on how to write all of our symbols mathematically so that you can have it look as it's supposed to be and formatted correctly. That's actually part of the rubric in quarter 2's writing assignment, is that you've actually put the symbols in and you've made it look like a semi-professional paper. It's 10% of your grade, so it's good to get this started today or as soon as possible. And I would like you guys to all practice it, and I will make that available for you on Friday as part of your bonus problem set. Okay, so one big thing in math, we never say I. You are not standing alone proving these. You're using countless other people's work, ideas, proofs. Everyone that's been involved in your life has gotten you to this point. So we credit everyone, and we use the word we, never I, because I have not done any of this by myself. So we always start with we assume. Assume means we're looking at the hypothesis, and whatever is given there in our picture or our if-then statement, we're going to use that right now. So it says we assume that lines A and B intersect with each other to form angles 1, 2, 3, and 4. So let's just kind of look at what that looks like. And I'm already starting to have a suspicion here that we're looking at the vertical angles theorem. So here's line A, here's line B. Let's label them. So again, line for L, and that's line A. Oh, and I double it up on that line. So let's go to this one and make that line B. Don't want to double label a line. And they intersect each other to form angles 1, 2, 3, and 4. Angles 1 and 2 form a linear pair. So I know that they have to be a linear pair, as well as angles 2 and 3. And we can see that angles 1 and 2 and angles 2 and 3 are linear pairs. Thus we have, using the supplement postulate, which states that if two angles form a linear pair, then they are supplementary. Angles 1 and 2 are supplementary, as well as angles 2 and 3. This is a very beginner's proof, right? It's just saying that we are going to use linear pairs. And what this is really doing is priming you to move into a vertical angles theorem proof. But let's see if what we have here is true. Would the measure of angle 1 plus the measure of angle 2 equal 180 degrees? Well, yeah. We know that they are a linear pair, and by definition. So you can see that we explained that already. But now we have to show the math. And when we do that, we always make sure we center and only show the steps. If I needed to put another sentence in between these, I would go back over here to the left-hand side, start a paragraph. All of your work that you did in your 2-column proof, and this is why I always start with a 2-column proof, can be used. You go down your Q side and you start with your givens and each of your conclusions. And as you do the conclusions, you need to show the work from your hypothesis in what's called block formatting. And that's where it's censored and stands alone. And this is also why we always double space. Does the measure of angle 2 plus the measure of angle 3 add up to 180? For sure. Now, let's say I wanted to do the vertical angles theorem. Well, what I can say then is if the measure of angle 1 plus the measure of angle 2 is equal to 180, and the measure of angle 2 plus the measure of angle 3 is equal to 180, by substitution, I can set the left-hand sides equal to each other. And through the subtraction property of equality, I am now left with the measure of angle 1 is equal to the measure of angle 3. And that's what the vertical angles theorem tells us. This angle is congruent to this angle, and this angle is congruent to this angle, which we'll go ahead and label as angle 4. So if we wanted to, we could borrow, and this is why we don't say I, we say we. We can set up a vertical angles proof almost exactly the same up to here. What we would then need to do is say something like, and we will show angle 2 is congruent to angle 4, and then angle 1 is congruent to angle 3, thus proving the vertical angles theorem. So this is really what this is all about. Just putting everything we've kind of talked about, all of our reasoning skills together, and coming up with a full-on proof of it. So like I've said, your next writing assignment relies heavily on both of these styles of proofs. Your homework are going to look like this. Fortunately, though, for the homework, you're going to have a lot of drop-down menus with options. So use your prior knowledge to make educated inputs there. And we're going to actually look at a couple of the homework problems at the end of this. But as I've said in class and on the Zoom meetings, this section does have some inherent ordering difficulties regarding our content. I can either present you with a bunch of theorems ahead of time, and then around the end of quarter 1, go back and show you why these are all true, or how we built them, or just the whole idea, the whole foundation of geometry for the logic portion of the class. Or we can get the logic ahead of time with a few theorems we may not have heard of, and then I can spend some time today showing you some of the theorems so that we can move forward. The theorems I'm going to show you are going to be heavily relied on during section 2 of our class, and I'm pretty sure the first one up is the vertical angles theorem. But most of our classes going forward are going to be introducing a couple theorems and then showing examples of how they work, working with them, and then moving on. So up first, we have the vertical angles theorem. And with that, I like to think of this kind of as the hands on a clock. If I were at, 12:05, I can imagine that these are extended. And then this one and this one are equal. And then this one and this one are equal. We'll overshot that. That's pretty much what it's showing you here. These are always, the vertical angles theorem just makes linear pairs. And it tells you that on each side of a line, so on each side of line 1, if I have 167 here, I have to have 13. And if I have 13 on that side with 167, on the opposite side of the line, I have the exact same thing. If I were to look at line 2, now my 13 associates here, and then I have it again here. And you can see in the diagram that they're color coded for us. So it's a little harder to see that, but here's another good, this is one of the more regularly used linear pairs, 120 degrees. Right, that's my obtuse angle. Here's my obtuse angle. See that they have the same value by the vertical angles theorem. And then my two acute angles by the vertical angles theorem are also the same. And this kind of makes sense. Think of this as if these are two pencils, and you put them together as a T. As you rotate the pencils without moving the center points, the angle changes, but its opposite side changes at the same time so that they're always matched. And this is kind of what I wanted to show you here. Earlier, this one's 90, this one's 90, this one's 90, this one's 90. The sum of that is 360 degrees. And notice that the tick mark makes a circle. That's actually by no accident why these are designed that way. We could also draw here our perpendicular symbol. And by the vertical angles theorem, if this one's 90 degrees, then this one's 90 degrees. And by our linear pairs theorem, this one must be 90 degrees so that these two add up to 180, and these two must add up to 180. So we can also end up with a square on the inside, and the interior angles of a square also sum up to 180 degrees. So let's look at a 2-column proof for this. So again, a theorem is a conjecture that is just proven. So now we can start doing proofs here. You can go back to the previous slides and start writing proofs from those. But let's see, given, okay, we're going to use the vertical angles theorem to prove that two things are true. That angle 1 and angle 2 are vertical angles. Now, they were kind of nice to you here, and they actually associated these vertically with each other. But just because the English definition of vertical means up and down doesn't do quite enough for our math class to prove it, but here's how we can do it. So it says given 1 and 2 are vertical angles. So notice that the first step here is that angle 1 and angle 2 are vertical angles, and that's our given. Perfect. So statements, we won't write that. We're going to write P and Q. The measure of angle 1 plus the measure of angle 3 is 180 degrees. And the measure of angle 2 plus the measure of angle 3 is 180 degrees. And they're saying that's by the supplementary angles theorem. What else could we call that? Well, 1 and 3 and 2 and 3. Or we could write the linear pairs theorem, right? So again, two different answers that mean exactly the same thing. So we do have more freedom in this class. But now we need to verify that that's true before we move on. 1 and 3 are in fact linear pairs and would add up to 180. 2 and 3 would also add up to 180. And then again, because they both equal 180, we can set the left-hand side of both of these by the transitive property of equality, or substitution would be another way, right? Because you can substitute the value for 180 for this, or you can substitute that for 180 there. So again, another option. And we show that that's true by the subtraction property of equality. We can get rid of both of angle 3's, and we've done everything we've set out to do. The only thing that I said sometimes you could start would be P6 and just show that Q6 is our conclusion. Again, you don't have to do this. There will be some professor sometime in your life going forward that potentially will. So I want to keep that at least available to you. All right, let's look at another theorem. And of course, you guys can pause this since it's on a video and you have time to copy it down. Congruent supplements theorem just tells us that if two angles are supplementary to congruent angles or to the same angle, then they are congruent. So that's a pretty confusing way to look at it. What it's saying here is if the measure of angle 1 plus the measure of angle 2 equals 180. So if I were to move this one over so that their vertices were matched, I would have a straight line. What it's saying is that I can then move angle 1 out and slide angle 3 so that their vertices are matched. And I would also have a straight line. Because both angle 1 plus angle 2 is equal to 180 and angle 3 plus angle 2 is equal to 180, I can say the measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 3 plus the measure of angle 2. And by the subtraction property of equality, I am left with the statement the measure of angle 1 is equal to the measure of angle 3. And that is our conclusion. So right there, I can take what's on our screen and make that a 2-column proof. And then I can turn that 2-column proof into a written paragraph proof. Wouldn't be much of a paragraph, it'd only take 2 sentences other than the setup and the closing. But that's exactly how we do that. Our next theorem is the congruent complements. So let's talk about the difference between supplements and complements. Supplements means adds to 180 degrees. Notice when I move these into the position, they complete a straight line and add up to 180 degrees. What complements means is that they add to 90 degrees. So if two angles are complementary, they add to 90 degrees. So again, if I take two angles and when I put them together, so if I move angle 1 to here so that their vertices touch and that these rays are directly on top of one another, if I get 90 degrees out of that, and then I can flip 3 over, associate it so that it's in the same fashion as angle 1, and slide angle 3 into there, and it also gives me 90 degrees, then angle 1 is equal to angle 3. Basically what this is telling you, algebraically, since we're kind of fresh into geometry, if x plus y is equal to z. Alright, let me apologize for the jump there. I chose to use a Greek letter for this example and realized that might be a little bit too much here. So let's go back to if x plus y equals z and a plus y equals z, then I can say since these two on the left hand side are both equal to z, they are equal to each other. And I can subtract out my y's and I get x is equal to x. Of course x is equal to x, but x is equal to a. And that's pretty much what we're doing here, except for now, instead of our variables being 1 character, there are 3 characters here. But they're still variables nonetheless. These are stand-ins for whatever measure of angle 1 is. So let's look at this if it were to be numbers. Let's say that the measure of angle 1 is 30 degrees. Well, for measure of angle 1 plus the measure of angle 2 to equal 90, I can say that 30 plus the measure of angle 2 is equal to 90, and get the measure of angle 2 is equal to 60. But now that I know this is 60, this also must be 30. And it shows that these are in fact congruent. So that is our congruent complements theorem. A lot of this stuff is things that you've learned in late elementary school, early middle school. And when you ask, what are you going to use this for in the future? The answer is this moment right here, and showing that complementary angles add up to 90 and supplementary angles add up to 180. Up next, we have our first theorem with no name. It's called Theorem 1.4, I believe. Might be 1.3. No, it's 1.3 is on the screen, so 1.4. And this is not given a name because it's a pretty common sense one. So I'm going to flip over to that right now and give you a minute to copy it down. All right, so 1.4 basically says all right angles are congruent. The definition of a right angle is that it is 90 degrees at the vertex. So if the definition of something is that it's 90 degrees, then of course all right angles are congruent. It's going to be a tough day on a proof if you are stuck and that is something that you need to tell everyone. But this is more of a it's good to know that all right angles are congruent to each other. Anytime you see this, or this, those are all 90 degrees. They're all equal to each other. This box again means 90 degrees. So that is theorem 1-4. We can call it the right angles congruency theorem, but it takes longer to say that than it does to make sense of it. Theorem 1-5. If two angles are congruent and supplementary, then each is a right angle. What does that mean? Well, are there any other numbers besides 90 plus 90 that will give me 180? Because remember, if two angles are congruent, if they're not congruent, we're not testing our hypothesis correctly. So here's 1, here's angle 1, here's angle 2. If they're congruent, then and supplementary, so if I add them together, the only way that can happen, let's do it visually really quick, is if I combine them, and then I can see that they make a straight line. So theorem 1-5 again, it's a pretty obvious theorem to look at. If two angles are the same measure and they add together to make a straight line, well, if I know they're the same and I know their sum is 180, I can just divide it by 2. Both must be 90 degrees. All right, so we're going to knock out a lot of theorems today. We have our linear pairs theorem. Let's formalize it. This is our 6th theorem on the screen, and we've already talked about this one. We just know that if we have a straight line and an angle or a ray that bisects it, no, we can't say bisects. That's later on. You'll learn what that means. Intersects it or intercepts it, whichever way you want to look at that word. The sum of those two angles is always going to be 180 degrees. Got a few examples up here. 139 plus 41 gives me 180. 90 and 90, this is 180. This also shows us that all right angles are congruent, and congruent supplements must be 90 degrees. 86, 94 takes one extra step mentally to add the 6 and the 4 to turn that into 100, and you get 180. And 53 plus 27 is 80. And with that extra 100 tacked on the front there, we again have 180 degrees. Now we're going to move on to talking about contradictions. Indirect proof is where you say if something, but if then, but we're going to assume that then's not going to happen. We're going to show it's actually going to happen. And then we're going to show that the assumption has led to a contradiction. And then that is going to conclude that Q must be true. This one is best done by just looking at a problem here. And that problem is if Alani walks more than 8 kilometers, so we have our if. So let's go ahead and color code this. Blue has been our hypothesis, so let's get back to that. If Alani walks more than 8 kilometers over a 2-day period, and then in our conclusion is green, then she walks more than 4 kilometers on one or both days. So let's think about what that means algebraically really quick. So our P is, let's not do that in green because that would be confusing. Our P becomes, let's do it on this slide here. So first we're going to identify the hypothesis and the conclusion, which we've done. Our hypothesis is Alani walks more than 8 kilometers over a 2-day period. And our conclusion is she walks more than 4 kilometers on one or both days. And the statement does follow the P implies Q format. So step 2 is let's show that the assumption, not Q, right? Remember we read this word here. as not Q leads to a contradiction. So look how we have to change, or let's look at it and then we'll look at how we have to change it. If Alani does not walk more than 4 kilometers on either day, then the total distance she walks over the 2-day period must be less than or equal to 8 kilometers. And this contradicts our hypothesis. So now let's go back through it and look at it algebraically. So if Alani walks more than 8 kilometers over a 2-day period, so 2 times D, right, 2 days, is greater than 8 kilometers. Our hypothesis is that on day 1, she walks more than 4, and on day 2, she walks more than 4 on one or both days. So both days has to be at least greater than 4. So let's assume this is not true. Let's say that day 1 is equal to 4 and day 2 is equal to 4 kilometers walked. Well, would her 2 days then be greater than 4 plus 4? Right, here's day 1, here's day 2, and in 2 days she needs to walk 8. Is 8 greater than 8? No. And this is a contradiction. What if I did less than 4? Right, I can pick any number less than 4. Well, then we can see right away if she walked 3 kilometers on day 1. Let's erase that. Well, let's just do it down here. So now she needs to walk more than 8 in 2 days. And she has 3 plus 4. And that gives us 7. So now you're going to probably say, well, what if we just said she did 10 kilometers on one day? Well, then we have to go back and consider that we have to negate this conclusion. She does not walk more than 4 kilometers on one or both days. So we have to keep it under 4 for both days. And that's what we've done. Here we have day 1 at 3. Here we have day 2 at 4 for a total of 7. So we've now run into a contradiction here. She must walk more than 4 kilometers on one or both days for this to be true. All right, so let's look at a word problem that's basically and strictly English, right? There's not too much math involved with this one, but we're going to use our reasoning here to try and figure out who Beth is having dinner with. So let's read the problem. Beth is having dinner with Sarah and one of Sarah's friends, Libby, Kelly, or Mercedes. Beth orders a chicken and spinach pizza to share for dinner. Who is having dinner with Beth? So we got to look at a couple things here. Libby is a vegetarian, Mercedes is at the library, and Kelly is allergic to mushrooms. So now we're using our indirect reasoning to determine who is having dinner with Beth. So the best way to look at this in a mathematical sense that I've tried to prime you with in the previous slides is, do any of these set up for a contradiction? Oh, Beth is having dinner with Sarah, so that's definitely a go for. Let's fill out our hypothesis first, or let's look at our givens. Beth is going to be at dinner. Sarah's going to be at dinner. But which of Sarah's friends will be there? Well, let's look at the outcome here. They order a chicken and spinach pizza to share, so they're all eating it. So whoever's there is going to be eating it. Libby is a vegetarian. So Libby being there leads to a contradiction of our conclusion, right? Because Libby would not be eating a chicken pizza. Mercedes is at the library. Libraries are expanding their services to survive in an ever-changing world, but I'm not sure that many libraries are serving pizzas and holding dinner parties. So Mercedes being at the library probably means she's not at the pizzeria. And Kelly is allergic to mushrooms. Well, there's nothing here about mushrooms, So Kelly would be safe to eat this pizza. She's not a vegetarian. Spinach is not a mushroom. So it looks like Kelly would be our best bet at the third friend. So let's see if we can do this. Oh, yeah. Just like we said, Libby cannot eat pizza. Mercedes is at the library. No mushrooms on the pizza, and other options have proved to be false. So that is not actually a very strong standing point, right? We can't just say because we've run out of options, the last one standing is automatically right. Ideally, if you're testing stuff and you're using your education and you're bringing everything together, your last option is going to be the one that you've used all your previous knowledge to determine is likely the least likely to be the right answer. Of course, here we're just ranking 3 friends of Sarah who will be having dinner with Beth. So putting Kelly last had nothing to do with the value of Kelly, but mathematically, in the order that we offer them, Libby to us would be the best bet. Mercedes would be a close second, and then Kelly is our last hope, right? These are 3 conclusions that we hope work. We're not completely convinced that Kelly's being the third option is going to be the one, but because this is just the word problem and we just need to think through it, the order or ranking of how likely these are to be true is not impacted. All right, so let's look at our first homework problem from 1.7. It's asking us to find the value of the variable and measure of each labeled angle. And knowing the vertical angles theorem now, we can say that x plus 12 is equal to 3x minus 24, because by the vertical angle theorem, these two are congruent and these two are congruent as well. So if I set these equal to each other, I can now solve for x. What I'm going to do is, since I have a negative here, I'm going to move it over, especially because my coefficient in front of this x is 1, and that's not going to leave me with a negative x. This is going to leave me 36 is equal to 2x divided by 2, and x is equal to 18. The reason we can now do this is because we know the vertical angles theorem, and we know that those angles are congruent. Let me show you that one more time. Vertical angles theorem says, I'm just going to write them in this fashion. 1 is congruent to 3, and 2 is congruent to 4. And since that's true, we can set them equal to each other and solve for x. All right, so the answers are already on the screen for you, but let's talk about why these are the answers. So it says write a 2-column proof of the linear pairs theorem. So as we know, the linear pairs is just if I have a line that has a ray or even another line or line segment passing through it that generates 2 angles, then angle 1 plus angle 2 is equal to 180 degrees. So here they've said if ABC and CBD are a linear pair. So let's label this. I have ABC and I have CBD. Notice that B is the vertex on both of these. That's a really good start on making this proof happen. So now I can make this one A to B to C, and then from C to B to D, right? Just to set it up. Our linear pairs. Does this look like they're going to be linear pairs? Absolutely. I can take this one plus this one, and that'll give me the entire angle. So I can see now that my 2 purple angles plus or added together will equal my green angle of 180 degrees. But we don't have to do all that anymore. We're just trying to write a proof. So here visually we can see that the measure of angle ABC plus CBD is equal to 180. We have visual proof. We've done it on this lesson already. You've done it in your homework. So you can just say that yes, by the linear pairs theorem, this is true. Now, this is a slightly new thing for us. ABC and CBD are supplementary. Well, what is the measure of the angle AD? Well, in green there, we have 180 degrees. And just like we learned in our protractor postulate, I can add my first purple angle plus my second purple angle together, since they share BC, which we can see right here, where this one ends. Right, BC, the next one begins, CB. Even though it's reverse order, we know they're the same. They also share this ray right here by my drawing. So yes, by the definition of supplementary angles, we are good to go. And that is your two-column proof for linear pairs theorem. All right, let's look at writing the first step of an indirect proof. Remember, indirect proof is we're aiming for a contradiction. So our statement is at least one line is parallel. So if I have 3 lines, let me switch to the writing tool. So I have line 1, I have line 2, and I have line 3. So it says at least one line is parallel. How would I write a contradiction there? Well, I want to assume that none of the lines are parallel, and then my task there is to show that at least one of the lines is parallel to another line or something else, and that will create that contradiction for me, right? At least one line is parallel means if I have line 1, line 2, and line 3, I can say assume temporarily that none of these lines are parallel, and then I'm going to show that they are in fact parallel. And to do that, I can use a theorem that we'll learn in the future, but I'll show you really quick. It just says if 2 lines are perpendicular to the same line, then they're parallel to each other. So since line 1 is perpendicular to line 4, and line 2 is perpendicular to line 4, then line 1 is parallel to line 2. And if you think about that, wherever you're sitting right now, if you have a door or a window nearby, this will work. This also works, you're obviously watching this on a computer. If you look in the top right corner of your screen, right, up here, if I were to call this a line, it's parallel with the very bottom of my screen, right? But if I go to the top corner, it's perpendicular to this vertical line. And since the top line going horizontally is perpendicular to my vertical line, and my bottom of my screen horizontal line is perpendicular to the right hand side as well, then my top and bottom are parallel to each other. That's all that theorem tells us. That's actually called Theorem 2.9, and that one is definitely on your writing assignment. It's also on the proof video that I show you on how you can take one picture and pretty much find any of the proofs that I'm asking you to find in just about any picture. But we'll definitely go over that more in class when we get there. But here, we can now show that these lines are parallel, and we've set up the contradiction. So at least one of the lines is parallel. All right, here's another one for indirect proof. I want to keep practicing these because these are very important. These are your contradictions. And what it says is write an indirect proof for the following conditional about the figure. So here's what we're actually looking at when we're doing this problem. And it says if EFG, so that is from E to F to G, and H to F to J are vertical angles, which they are, right? This hypothesis is true. By the vertical angles theorem, they're going to be congruent. So we can say that's true because of the way that this diagram was drawn. Then X does not equal 3Y. So remember, we want not Q for our contradiction to be possible. And then once we can show that the contradiction happens, we can then say that the overall value is true. So to prove this given conditional by contradiction, assume EFG and HFJ are vertical angles, and look here, X equals 3Y. So that is the negation of X does not equal 3Y, right? What's the opposite of does not equal? It is equal. Because EFG and HFJ are vertical angles, again from our hypothesis, they are congruent, and we're going to say by the vertical angles theorem. This means their measures are equal, again, by the vertical angles theorem, yielding the equation x plus y equals 2x minus y. And what we need to do now is a little bit of algebra. But notice, now that we're in geometry, they're not actually asking us to do that. This is what they call in higher level math classes. This is a trivial piece, or this is a exercise left for the reader. Never again until you get into much higher level math classes will your teacher say, let this be an exercise for the reader. If you get to this point, this is Algebra 1, pre-algebra stuff, it's just manipulating the equation. I am okay with on your writing assignment saying an exercise, this is an exercise left for the reader. And I wrote ready. Let's just back that one out there, guy. All right. But I'm going to go ahead and show you that. Go ahead and show you what this looks like when we balance it algebraically. I don't like this. I'm going to show you what this looks like algebraically. So I'm going to get my x's by themselves, but I want everything to be positive if I can. And that means if I move this over, I'll be left with just x. And if I add this over, I'm just left with plus y. Gives me positive 2y. X is equal to 2y. So we have a contradiction here, right? We said, so here's our contradiction. Here, our negation said x equals 3y, which does not equal. And we have shown, so here's that word we again. By contradiction. That. And then we just rewrite the conditional. Is true. Now, do we have a full-fledged theorem here? No, we have not shown this for all cases. All we've proven right now, all we have actually done is show that x does not equal 3y. But that is an indirect proof for this problem as it's written for us. So at least we have that done, and we can move on to our next problem. And we're going to look at one more. Write an indirect proof for this conditional statement about the given figure. So our hypothesis is if NJ is the perpendicular bisector of KM, so this is P, and Q is LM equals 6. So right here it's asking for the given, and that's why I'm not negating anything yet. Identify P and Q as it's written. So our P we just bring down here, our Q we just bring down here, double check that I filled that out correctly, we're good to go. One type of indirect proof is proof by contradiction. I know I keep saying we're going to use proof by contradiction as indirect proof. That is our main one. We also have contrapositive and a few others, but you're not going to need them for this course. I'm actually editing out most of those questions because we are missing a week in this school year, so you don't have to worry about that. So the first step of a proof by contradiction is to assume that P is true, or assume P and not Q are true. So that goes back to our truth table. and we want P is true and not Q is true. But we need to show it's false so that we can get that the overall truth value of this is false, and therefore our original conclusion is potentially true. So if in this case, assume that NJ is the perpendicular bisector of KM. We did not change our hypothesis, but we did negate our conclusion. LM equals 6. Negated is LM does not equal 6. The given figure, so this is part of our hypothesis here because it was given, is that KL equals 6. This means that KL does not equal LM. So L to M. So we can, what it's saying here is I cannot put a tick mark on either one of these. If that, it follows that NJ does not intersect KM at its midpoint. So this is the caveat there that we can say does not happen. So L is not the midpoint of KM, and NJ cannot be the perpendicular bisector of KM. Now, we don't know the word bisector yet. This is why I have this as a homework help problem. The bisector means it cuts it in half. Bi means two, and sector, we'll just call portions for now. So bisector means two equal halves. And basically this whole proof is saying that if we cannot say that these are true, then this cannot be cutting it in the middle. It is the perpendicular interceptor, but it's not the bisector. This contradiction contradicts the assumption that P is true. NJ is the perpendicular bisector. The proof by contradiction is therefore complete, and the given conditional statement has proven to be true. So basically, this whole problem boils down to this. Boy, that takes a lot to undo all that. So let's look at exactly what NJ, that's this guy right here, is the perpendicular bisector of KM. For that to be true, NJ must cut KM into two, that's a snake, two equal pieces. Okay, so that's all this is saying here, is that NJ must cut KM and KL and LM into two equal pieces. So I can put this and this. Then LM equals 6. Oh, that would make it true, and it keeps it consistent with both the tick marks and the values. So we can say it's true, but we need to do it by contradiction, or we need to do it by indirect proof, specifically a contradiction. And that's where we come in and say LM cannot equal 6, which then means these cannot be congruent. So LM can be any value other than 6. This is the same thing as if your parents say, you asked to go out and do something. They said the deal was, if you clean your room, then you can go. And you say, I did clean my room. Then they say, then you can go, but they check and your room's not clean. And now they have shown you through contradiction that you did not satisfy this overall, and you cannot go.